if you don't mind, Hippo.
Oh, of course.
Cool.
I mean, if it's bad, don't put it on YouTube.
Okay, we can discuss about this later. Let me know. We can also cut, if there are questions.
Yeah, okay.
We can cut some parts. All right, so welcome everyone. I'm very happy today to introduce Hippolyte Dourdent, who's a colleague of mine. We share the office, although we've almost never been to the office due to the pandemic, but we stayed in touch anyway. So yeah, Hippo is going to present a paper, very nice paper, I believe, called A Gödelian Hunch from Quantum Theory on Why the Measurement Problem is a Self-Referential Paradox. Stage is yours.
Thank you very much for the introduction. So yeah, to give you some context, so I'm going to present you, what I'm going to present you is based on a paper that I wrote for last year FQX essay contest, and I had the chance, so I won the third prize to this essay contest. And so it's going to be published soon in a book with the author winning essay. And so the topic of the contest was understandability and computability and unpredictability. And so the topic was basically, there are some rigorous arguments that show that what we can prove, predict, or compute is limited. And so do these arguments, do these results, like for example, Gödel's theorem, has any implication for physics? This was the topic of the contest. And so my essay, of course, tried to kind of answer this question. So here is the outline of my talk. So first I will talk to you a little bit about my main motivation. The question, is physics paradoxical? Then I'm going to present you so what I called Gödelian Hunch and try to analyze the measurement problem in the light of this Gödelian Hunch, measurement problem and the Wigner-French thought experiment. If I have the time, I would also like to say a few words about contextuality, the RD paradox, and analyze the Frauchiger-Renner Paradox to give you my view on this new paradox. If I'm too short on time, I will go directly to the last section, where I will try to maybe just compare my view with the already existing interpretations, whether they are realist or anti-realist ones. So of course, if I'm not clear at some point, don't hesitate to ask me clarification questions. And yeah, I hope we will have a nice discussion after the talk. So let's start with my motivation. So I don't know if everyone knows about this article from Ernst Becker. So it's entitled "The Logic of Non-Simultaneously Decidable Propositions." It was published in 1960 in the review in the Dialectica. And so basically this is a seminal paper for quantum contextuality. This is the first paper where the Cohen-Specker results appears in the literature. So it's 7 years before the Cohen-Specker paper, but the result is already in this paper. At least maybe not proved really rigorously, but it's enunciated. And so there is an epigraph to this paper, a motto put here by Specker, and it's a quote from Ferdinand Gonset, who is a Swiss philosopher. And it's the following one: La logique est d'abord une science naturelle. So logic is at the first place a natural science. What does it mean by that? Actually, so shortly, Gonset defended the idea that logic might be empirical. The idea that logic might be just, or at least some kind of logic, might just be some kind of an empirical refutable science of any object whatsoever. And Specker kind of agreed with these points. And of course, so maybe some of you know that there was, so a few years later, this famous debate between Putnam and Dumet on the exact same question, is logic empirical? So Putnam defended the idea and Dumet was against the idea. And it's basically the idea that if logic is empirical, and if quantum theory in some way is going against classical logic, so maybe we should revise classical logic on the quantum results that we get. So I'm not going to answer directly this question, is logic empirical? I'm more interested in the dual question or the mirroring question, is physics paradoxical? What do I mean by that? So if we take paradoxical or paradox in the etymological sense, so what goes against the doxa, what goes against the common opinion, well, the answer is quite trivial, right? Because I think we could all agree in some sense that scientific research in general is driven by paradoxes, is driven by something that is against common opinion. Otherwise, we won't research anything. Everything will be just, well, common opinion. And scientific theories are very often counterintuitive, whether it's quantum or not. I mean, almost every theory is based on something that is counterintuitive or paradoxical. This is why we want to search. So it's quite, in this sense, it's quite trivial. This is not what I'm interested in here, because of course, quantum theory goes against common opinion, but it also seems to go against classical logic. So the sense of paradoxical that I'm interested in here is a more precise one. It's the one of logical paradoxes, which can generate self-contradictory statements and things like this. So just to give you a quick reminder, the most famous of this one of this logic paradox is the liar paradox. So probably everybody knows this one, but I'm just going to remind you anyway. So what is the liar paradox? So we have a liar. We have a liar here, and the liar is enunciating the following sentence. The sentence is false. Why is it a paradox? Well, if this sentence is false is true, then the sentence is false. And if the sentence is false, then it is true. The paradox emerges from the fact that we have a self-referential structure, logical structure, and a contradiction. And this leads to a form of overdetermination because the sentence is both true and false. If it is true, it is false, and if it is false, it is true. And so if we define, give a really broad definition of decidability as the ability to associate a truth value to a sentence, a proposition, then we can say that this sentence, the liar sentence, is undecidable. There is a lot, of course, of various versions of this paradox. So one is the straightened liar paradox, where you have two liars, Alice and Bob, but it's basically exactly the same structure. You have self-reference, a contradiction, which is going to lead to some kind of overdetermination. So in the straightened liar, Alice is saying Bob's sentence is false, and Bob here is saying Alice's sentence is true. And so you see the circularity, and they're going to contradict themselves at the end. Okay, and so the liar paradox underlies really, really famous results in the foundations of logic. So the Gödel theorem. So again, a little reminder for everyone. So I'm not a specialist of logic. A disclaimer, I'm not a specialist at all. This is why I'm going to give some really broad view on what the theorem is, because I don't want to go into the mathematical details because I won't be able to talk about this. So. But so the Gödel theorem, so there are two Gödel theorems. The first one stipulates that a theory is sufficient to demonstrate the basic theorems of arithmetic is necessarily incomplete, meaning that there are statements which are neither demonstrable nor refutable. And these are called undecidable statements. The second Gödel theorem shows that a theory is consistent, so there is no contradiction inside the theory, if there are undecidable statements. And what I want you to remember for what is going to follow for my talk is the following. We can just take it as the broad sense that is underlying the Gödel's results, or the fact that who realizes the proof of the consistency of a well-behaved scientific theory must be external with respect to the theory, in the sense that she or he cannot use only the proof theoretical tools allowed by the theory. She must also use meta-theoretical tools. If you want to prove that your theory is consistent, you have to be external. You have to use theoretical tools that are not inside the theory that you're studying. Okay, this is really important. There is also another famous theorem in the foundations of logic that is also based on the layer structure, on the layer paradox structure. It's Tarski theorem. And this one stipulates that any description of the truth of a proposition must be made in a richer meta-language than the language in which the proposition is stated. So who grasps the concept of truth for a well-defined theory cannot only express himself in the language of the theory, he must use a higher order language, meta language. So yeah, I hope everyone gets what I mean by meta theoretical meta language, because it's going to be important for the rest of the talk. And so his physics paradoxical. I told you that I was going to understand the sentence with in the sense of logical paradox, for example, the layer paradox. And so now that I remind you what Gödel's theorem is, I can talk to you what I mean by Gödelian Hunch. So it's an expression that was coined by Sangolies in this paper, Epistemic Horizons and the Foundations of Quantum Mechanics, and is said, so in the paper, he says that the Gödelian Hunch is the idea that the origin of the peculiarities surrounding quantum theory lie in phenomena related or at least similar to that of incompleteness in formal systems. So my way to rephrase it with my own words, what a Gödelian Hunch is to say, what if the paradoxical nature of quantum theory could find its source in some undecidability, analog at least with the one emerging from paradoxes like the layer paradox. So it's quite general, it's quite broad, but this is a hunch. This is the idea that I want to argue for and defend here. So now that you know about my motivation, you know what I mean by Gödelian Hunch. Let's try to analyze the measurement problem in the light of this Gödelian Hunch. So you know that measurement problem, there are various ways to define it. There are arguably different versions of the measurement problem. The measurement problem I'm interested in here is what I call the what's in the box problem. So as Czeslaw Bruckner expressed in one of his papers, analyzing the quantum measurement problem, it's the question of what makes a measurement a measurement. There is nothing in the theory to tell us which device in the laboratory corresponds to a unitary transformation and which device corresponds to a projection. So we want to know, what do we put in the box? Do we put the device? Do we not put the device? To illustrate this, to be a little bit more clear, let's start with, on the one hand, with a qubit, okay? This qubit, so I didn't put the normalization here, but of course there is some normalization. We start with a qubit, and so for instance, you can just imagine that you send a photon on a beam splitter, and your qubit is what happens next, okay? So, and your qubit is inside this quantum box, okay? This is your quantum system that you want to study. Now, in this case, the measurement process is going to be described by a projection either on the 0 state or on the 1 state, okay? This is your device. You ask the question in the computational basis, is it 0 or 1? And it's going to be projected on either 0 with a certain probability or either 1. Okay. But on the other hand, you could say, okay, but these devices are physical systems. And in the theory, there is nothing that forbids me to also describe my devices as physical system and quantum system. So I can define a quantum state for my devices. And so the initial state M just means my devices are ready to perform or ready to measure. And so the same measurement process is now going to be described as a unitary evolution of this compound system composed by the qubit and the devices. And at the end of the unitary evolution, we are going to end up in a completely maximally entangled state, 0, 0 plus 1, 1, where you have, if the qubit is observed in state 0, then the device 0 click, and if the qubit is in state 1, then the device 1 is going to click. This is this state. And so here you see that what's inside my quantum box, what's in the box, is different than in the first case. Here, what's inside the box is both the qubit and the measurement device that are completely entangled at the end. And so the measurement problem arises from this fact. We have two ways to describe the same physical dynamics, the same process, the same measurement process in two different ways. And so we put in each, we have put something different inside the box, but is there a right description? Is there a right description? And how can we make sense about this? With just quantum theory, we have two ways to describe the same thing in two different ways. That seems to be contradictory. So maybe there is some tension, I don't know, in the formulation of quantum theory. So we can analyze this afterwards. Another version of this problem that I'm going to analyze is the Wigner's. This is actually what I'm going to analyze. This is the Wigner-Swan's thought experiment. And it's basically just a meta illustration of the same problem I showed you before. The Wigner-Swan's thought experiment wants to answer the question, what happens when an observer observes another observer observing a quantum system? So in the first case, we still have our qubits, and now we are just explicitly saying, so here is the observer. This is, we are going to call him Alice's friend or the friend. And so the friend is going to measure the qubit and the qubit is going to collapse, okay? So its measurement process is going to correspond to a projection, the collapse of the wave function. On the other hand, well, we have Alice, who is going to describe the compound system made of the qubit and her friend. And so in Alice's quantum box, we have the friend box, but the friend that is also inside the big box. And so she's going to describe this measurement process. So the measurement of the friend, she's going to describe it by a unitary evolution because it's inside the quantum box. She's going to describe it quantumly. And so the Wigner-Swan's thought experiment is actually the same problem, what's in the box. So we have two ways to describe the same process in something that seems to be contradictory. So for the friend, it's a collapse, and for Alice, it's a unitary evolution. Okay, so now I'm going to give you my analysis of this problem. I'm going to define the notion of theoretical object. Theoretical object is just an object described by the theory, so a quantum object, okay? So a qubit, for instance. We also have a meta-object, meta-theoretical object, and a meta-theoretical object is just an object that is using quantum theory, that is supposed to be outside quantum theory, okay? And I also define the term meta-context, which is just the set of the studied quantum object, so the theoretical object and the meta-theoretical object that is studying it. So in the first case, my object is a qubit. The meta-object is the observer, is Alice's friend. And the meta-context is the set qubit Alice's friend, okay? And so when he applies, so when he's measuring the qubit, it's going to be a measurement process described by a projection. And so the final set will be either 0 or either 1. On the other hand, we have this case where this time Alice seems at least a little bit different, right? Because she's going to be able to measure the compound system of an object and a meta-object. So we might want to call her a meta-meta object. Okay, we are it seems that we are in a higher degree of a higher level of abstraction. So we could start by saying, okay, Alice is a meta-meta object. She is a meta-observer. And so here the meta context is the compound system of the qubit and the friend, what's inside the box, and the observer or the meta observer, this time is Alice. And so she's going to be described what's happening in the box, so the measurement process inside the box by a unitary evolution, and the final state is going to be this entangled state. And so now we can try to see what are the underlying assumptions here. I'm going to propose a set of assumptions. I'm not claiming that it's complete. Maybe there are some hidden stuff in what but this is basically what I want how I want to derive the paradox. So the first assumption is universality. Universality means that quantum theory is correct and can be applied to any object. Another assumption that is crucial, according to me, is what I call non-meta contextuality. What does it mean? It means that the truth values that are associated with quantum proposition. So what I mean by quantum proposition is just the quantum states. The truth values that you associate with the quantum proposition are independent of the meta context. So the truth values that you are going to associate to this state are independent or considering this meta context or this meta context. This is kind of equivalent with the notion of observer independent facts by Chasler-Bruckner. And so if you assume these two assumptions, universality and non-meta contextuality, this corresponds to something that corresponds to absolute universality. And what is absolute universality is the fact that quantum theory is correct and can be applied to every object, irrespective of the meta context. So to give you an example, to show you what's how we can find a paradox from here, let's assume absolute universality. Let's assume that we have universality and non-meta contextuality. And now we are going to assume that we have an infinite chain of observer. This is actually the Feynman chain. So you just assume that you have an observer, a meta-observer, a meta-meta-observer. Okay, so we start by an object. We have an observer that is observing the object. We can put these two guys inside the quantum box. So we have a meta-observer. We can put her also in a box. So we have a meta-meta-observer. We put it in the box, meta-meta-meta-observer, etc., etc., etc. And you can go to infinity like this. And if you want, you could just assume that at the end of the road, you have some kind of ultimate meta-observer that you can call God if you want. It corresponds to some kind of Laplacian demon. So let's go with a demon. And so if such a demon exists, and if such a demon can measure the whole universe, so every object, so because we assume absolute universality, then the demon is necessarily excluded from the universe. Because if he's not excluded from the universe, you're going to have self-referential problems. He's going to just measure himself at some points. And so it's going to lead sometimes to some liar-like inconsistencies. I'm not inventing this, so there is a theorem that shows this quite rigorously. It's a Breuer theorem. It shows that if a theory, whether it's quantum or classical, it works for both. If a theory is considered to be absolutely universally valid, the theory cannot be experimentally fully accessible due to self-referential problem. And so there seems to be some kind of tension between absolute universality, so universality and non-meta contextuality taken together, in which the measurement process is described theoretically, and the notion of measurement in which measurement is treated as a meta-theoretical process. So try to be a little bit more clearer here. Assume that you have absolute universality, okay? So if you want to describe the whole universe, then necessarily, if you want to measure it, you have to be outside. But if you're outside the universe, you're not part of the universe. So your theory is not universally valid because you're outside of it. There is one object to you that is outside. So it means that if you want absolute universality, you cannot talk about measurement. You have to be inside the universe, okay? So you don't talk about projection at all. You just talk about unitary evolution and that's it. Everything is entangled to describe the wave function of the universe, the unitary evolution of the wave function of the universe, and you're just inside. You're just an object like any other object, but you're not an observer. And if you try to take the position of an observer, you're going to face self-referential problems. And yeah, that's it. And on the other hand, you can also play the other card where you're okay with abandoning some form of universality, absolute universality, and just talk about measurement as what it is. A measurement is a meta-theoretical process. So interaction between an object that is outside the theory, that is using the theory, and an object that is described by quantum theory, that you use quantum theory to describe it with. So let's go back to our Wittgenstein problem. So here is, according to me, the underlying three assumptions that are contradictory with themselves. So we have three assumptions: universality, non-meta contextuality, and measurement. And by measurement, I mean the fact that you have an interaction between an object and a meta-object. And this interaction is meta-theoretical. So, and by meta-theoretical, I mean you describe it by a projection. The projection is not at the level of quantum theory. It's at the meta-theoretical level. And so now we can just play the game which assumption we want to drop. So I'm going to say some stuff here. I'm not sure at all of what about what I'm going to say. So of course, for the discussion, we can just discuss this if you disagree with me. I believe that GRW is not quantum theory. I guess everyone agrees with it. So we can say that they just drop universality in some sense. Maybe also measurements, I don't know, but at least they drop universality. Because in universality, I'll assume that quantum theory is correct. This is not true for them. Hippolyte and many worlds, they just give up on measurement, or at least they should. It's quantum theory from inside. It's just absolute quantum theory that describes the evolution of the wave function of the universe. And so they should not talk about observer at all. And if they don't do that, they are completely consistent. And it's just quantum theory from inside. De Broglie-Bohm, I'm not sure at all. I guess they abandoned the projection. I'm not sure. And there is a form of extra contextuality in the Broglie-Bohm theory. And so I believe that in some sense, they are going to abandon something inside non-meta contextuality, but I'm not sure at all. I think that my assumptions are not super convenient to analyze the Broglie-Bohm theory. So we can discuss this later, but I don't really know how to interpret that. And of course, so the way I formulate it, in my opinion, the most logical solution, the most evident solution is to just give up non-meta contextuality. This is why I formulate this set, because I believe that's the most natural solution here is just to drop non-meta contextuality. And so acknowledge meta contextuality. What does it mean? Acknowledge meta contextuality means that you acknowledge that your theory is still universal, but not in an absolute way. It's universal in a relative way. It's universal with respect to a meta context. Okay. And so remember, a meta context is a definition of the set, what is studied and what is studying in some sense. Also, if you don't like the word study, it's what is quantum and what is not quantum. You just have to put a cut somewhere. The cut can be put anywhere. It's an undiscriminative cut. So it's the shifty cut that Bell was telling about. And so, it's a universal cut. You can really put it anywhere. And here, the notion of meta observer or meta object has no sense at all, because if you try to start building a hierarchy of observers, you're going to end up with the paradox I just showed you before with the Laplacian demand. So here, everything just needs two levels. Every description is two levels. The level of quantum theory, the level of the meta theoretical, and that's it. So everything is perfectly consistent inside this meta context. Everything is perfectly consistent inside this meta context, and you don't talk about meta object. Actually, Alice is just a meta object, and inside the box we have the object, the theoretical object, and that's it. And every question that you ask, if you are inside the meta context, if you ask question of what is happening in the other meta context, it's just undecidable. It's just, so you could say it's meaningless. We can also debate this, but it's going to raise just inconsistencies. To see that, I give the following illustration. It's inspired by Alexei Greenbaum epistemic loops. So just describe all the theoretical object of your theory by a loop. Okay, every point of this loop is going to correspond to a theoretical object. Now, when you cut the loop, you send an object inside the meta to the meta theoretical domain. So in our first meta context, we have the qubit that is on the loop, and we have sent the friend outside of the loop. He is meta theoretical, and is going to, when he's going to measure the qubit, is going to do a projection. Okay. Now, in the other context, the friend is on the loop. Is still part of the is treated quantumly with the qubit. Okay, and now the object that is outside of the loop is Alice. So she is the meta theoretical object, and here you have your object, theoretical object. If you ask questions, if you are, let's say you are in this context and you ask question, what is happening inside the box, and if you interpret the friend as a meta object when he's actually treated as an object, it's like you're just ignoring the cut. It's like you're ignoring meta-contextuality. You just go back to non-meta-contextuality. And if you do this, if you ignore the cut, and if you want to treat a measurement as a meta-theoretical process, so as projection, where you're just going to have self-referential paradox at the end. Okay, I don't know how I'm doing on time. Yeah, I'm going to be maybe a little bit quick, but I want to talk to you about contextuality. So I will take some time to do this. But so yeah, this was actually the main part of the talk. Okay, so now what I'm going to say is just to give some further examples, and that's it. So now I'm going to talk to you about contextuality. So a reminder, what is contextuality? So it comes from the Cohen-Specker theorem that actually shows that the quantum formalism cannot be extended in such a way that Boolean logic holds in the extended domain. Quantum logic is based on intertwined Boolean algebras that cannot be embedded in a global Boolean algebra. There has been a lot of work on the Cohen-Specker theorem, a lot of generalizations, graphical generalization, topological generalizations, ontological generalizations. One of the generalizations that I really like is the contextuality a la Abramsky, which is a topological generalization, where contextuality is seen as a logical obstruction. So contextuality emerges when you have locally consistent data that are globally inconsistent. A nice way to represent this in just a pictorial way, it's not rigorous at all, but just to try to picture what it means, is the construction of the Penrose triangle. So you imagine that you have your data. Let's say, for example, it corresponds to, I don't know, some observables, that you have 3 bars, A, B, and C. And you can form 3 local contexts with these 3 bars. You can, let's say, measure A with C. You can measure A with B. You can measure B with C. And each context is completely consistent. You see that you don't have any paradox here, right? But when you try to define a global context, you face some kind of logical contradiction. You see that you end up with a completely logical, impossible figure. And so this is the way that contextuality is working, actually. So in a similar way, I'm not saying that this is quantum theory, of course, but it's analog, at least. And so a nice illustration of this contextuality à la Abramsky, a nice canonical example, is the Hardy paradox. So what is the Hardy paradox? You have 2 players, Alice and Bob, and they share a quantum entangled state. So you have 2 qubits that are actually entangled. Alice and Bob can ask 2 questions to their own, to each part of their system. The first question is the computational question: is a particle in the 0 or the 1 state? The other question is the diagonal question: is a particle in the plus or minus state? And so the initial state of the particles is the following entangled state: 0, 0, plus 1, 0, plus 1, 1. And what is nice about the Hardy paradox is that you can really easily picture it with quantum optics. So I come from quantum optics, so this is where I really like to draw photonic circuits. And so you just imagine that Alice has a positron, Bob has an electron. The positron is going into a Mach-Zehnder. The electron is also going into a Mach-Zehnder, and you're just going to collapse them together. So join them. And so this is basically just like I don't know if you know this, but it's an Eliezer-Weidmann bomb, but with a generation to bipartite Eliezer-Weidmann bomb. And so what's happening is that if the positron is going on this path, the 0 path, and if the electron is going on the 1 path, they're going to meet. And if antiparticles meet, well, they destroy each other. And so this is why you don't have the state 0, 1 here. Okay, this is how you get 0, 0 plus 1, 0 plus 1, 1. They just annihilate each other in the middle. And so here the quantum system, so what's in the box, again, what's in the box is this, okay? And the quantum proposition, so what is your quantum description of what's happening in the box is this state. When Alice and Bob are going to ask a computational question both at the end, okay? So Alice and Bob are going to ask, is it 0 or 1, is it 0 or 1? And so you just write what's happening in the box in the corresponding context. And so you end up with this system. And of course, you can rewrite it depending on what they're going to ask. So before measurement, if Bob is going to ask, is it plus minus? And if Alice is going to ask, is it 0 or 1? You can just rewrite the previous state in the different bases. Okay, so this is before measurement, of course. This is what's inside the box here. But you can, and you end up with a new quantum proposition associated to a different context, measurement context. Of course, you can do it in the other case, and of course, you can also do it when they both ask the plus or minus question. Now, what we are going to do is we are going to add a meta-theoretical statement to the quantum proposition. So you have the quantum proposition, which is a theoretical statement. So it's just the quantum state, quantum theory. And now you're going to add a meta-theoretical statement on top of it. So for example, here, the meta-theoretical statement that we are interested in is Alice or Bob, it doesn't matter, but let's say it's Bob, is going to infer from this that they can both obtain the minus state. Okay, there is a probability of 1/12 that they are going to end up in the minus state. This is a meta-theoretical statement. Now we're going to do this for each context. Okay, so in the other context, here we have Alice, who is going to infer that if she has end up in the minus state, then it means that Bob gets the 1 state. Okay, so this is a meta-theoretical statement that you can infer from this quantum proposition. So you have this one also, where here Bob is saying, if I have 1, then Alice gets 1. And the final one, it's Alice who is saying, if I get 1, Bob gets plus. And of course, you can see now that, let's start from the beginning, with just looking at the meta-theoretical statements. Bob is saying we can both get minus. Alice is saying if I get minus, Bob gets 1. Bob say if I get 1, Alice gets 1. And Alice says if I get 1, Bob gets plus. And it's completely contradictory with the starting point. And so this is what Abramsky and et al. Are calling a layer cycle. This is not actually the layer paradox, of course, but it's kind of analog. You have some kind of loop, and that is contradicting itself. And so what is the conclusion from this in the light of my Gödelian Hunch? Well, if meta-theoretical statements are attached to quantum proposition, they cannot be embedded in the global Boolean proposition in general. By global Boolean proposition, I mean global classical proposition. And so if you want to associate a truth value to quantum propositions, the meta propositions are infected in some way by the non-Boolean logical structure of quantum theory. And they become just globally indecidable and can potentially lead to some kind of logical contradiction analog with the layer. And this is why, how I argue for Gödelian Hunch from quantum contextuality. Okay. And so now that I presented you the Wigner friend and the Gödelian Hunch from the Wigner friend, I presented you contextuality and the Gödelian Hunch from contextuality. Now I can talk to you about Frauchiger-Renner Paradox, which is just a mix of these two guys. So you may know that in the field of quantum foundation, nowadays there is a renewed interest in the Wigner friends for the experiments. Why? Because recently there has been a lot of work on some kind of new hybrid paradoxes that are just mixing a quantum paradox, or paradox, yeah, let's say it's a paradox. So that are all are based actually on some form of contextuality, contextuality at Abramsky. And they just take this quantum paradox and they just mix it with Wigner friend. So we have different examples. So there is this paper by Czaslaw, a no-go theorem for observer-independent facts, where he Wigner friendify the CHSH inequality and also the GHZ argument. You have the most famous one is the one by Frauchiger and Renner, where they just Wigner friendify the RD paradox. You also have a work where Villasini, Noria, and Lilia Del Rio generalize those results to describe them in a GPT framework. And they also given as an example a Wigner friendification of the PR box. And so I have personally worked on the Wigner friendification of a Cohen-Specker theorem with the Marvin Perry square. but recently just have been put on the archive, so I'm going to stop working on this. But yeah, Sangolius has also done this so with the Marine-Perez square. Okay, so but we are going to talk about the most famous one, who is this guy. So what is a Wigner-Frenification? You just take your qubit, so your computational basis. You have here the observer, the qubit is going to measure it in the, if it measure it in the 0-1 basis, the Wigner-Frenification is just this thing. So you're just going to have a meta observer. So I have not abandoned any assumption here. So I'm still going to talk about meta observer for now. So you have Alice, the meta observer, who is just going to measure in the computational basis, this computational basis, the qubit, the compound system of the qubit and her friend. And so you can interpret this basis as an observer level basis. Why? For Alice at least. Why? Because it's kind of, it's like Alice is just asking her friend, did you find 0 or did you find 1? And but they are, it's going always to be consistent. If the friend as 0, it's going to observe 0, so it's going to be the 0-0 state. And if he observed 1, it's always going to be the 1-1 state. So at the end, you just asking what does the observer observe? What does the friend observe? So this is why I call this an observer basis. You can also Wigner-Frenify, of course, this is the most important part. You can Wigner-Frenify the diagonal basis. So here it was just a measurement in the plus-minus state here, but now in the at the meta level, you assume that it's still a computational basis, computational measurement inside the box here, but it's Alice who is going to measure the compound system in the diagonal basis. This is really important. And now she's going to actually perform some kind of quantum measurement on the compound system of the qubit and her friend. So this is this definition. And you can interpret this at the meta observer level because it cannot be interpreted at the observer level, of course. Here the friend is described quantumly with the qubit. And so what does the Frauchiger-Renner paradox do? It's going to take every quantum proposition from the RD paradox and Wigner-Frenify them, okay? And just rewrite them according to what I just showed you, the transformation I showed you. So if you have the 1 plus 0 minus state, you're going to have the 1 1 plus 0 0 plus and 0 0 minus state. And here you have to be careful about the Hilbert spaces you're considering because when it's computational basis, it's an observer basis, so it's the system and the friend. But when you have the diagonal basis, now it's really the meta at the meta level basis, at the meta observer basis. And so you have done this with the quantum proposition, and you're also going to do this with the meta theoretical statement. And so in this case, we say that if Alice gets 1, Bob gets plus. This corresponds to this. And this is going to be now interpreted as if Alice's friend gets 1, then Bob gets plus. Okay. If Alice's friend gets 1, then Bob here gets plus. And so, of course, we have the previous layer cycle that I showed you. And now we're just going to Wigner-Frenify all of this. And so we have Bob who is saying we can both get minus. Then Alice is saying, if I get minus, Bob's friend gets 1. Bob's friend say if I get 1, Alice's friend gets 1. And then Bob's friend is saying, Alice's friend is saying if I get 1, Bob gets plus, and it's contradicting the first statement. And this is how you have a contradiction. There is two differences with the RD paradox and the Wigner friends. Here, in the RD paradox, you could interpret it as something that is fully contingent. And actually, it was only statements that you could associate with Alice or Bob, but that's it. Here, you have each statement that is associated with a different observer. So this is one point that is really interesting here. And also, unlike the Wigner friend, for the experiment where it seems that there is some contradiction, but there is no really logical contradiction. Here you have a logical contradiction that comes from the RD paradox section. You have just a logical contradiction. And so how to interpret this? So in their paper, they propose the following set of assumptions. So universality, quantum theory is correct and can be applied to a system of any complexity. Consistency assumption, observer and meta-observers should be consistent with each other. And a single outcome assumption, measurement yields a single outcome. This was a lot debated in the literature, especially the consistency one, who is quite weird. And actually, so I'm just going to give you my take on this. I believe that there are two things that are underlie this assumption. The first one is non-contextuality, because to derive the paradox, it's really based logically on the RD paradox. So you have to assume some form of non-contextuality at some point. So the fact that truth values associated with quantum proposition are independent of the measurement context. And so for instance, if you're a Bohmian, since Bohmian mechanics just drops non-contextuality, they just fine with the Frauchiger-Renner paradox because they have contextuality. And so they just give up on this one, but they're not giving up of something really strong. They're just saying, yeah, well, our theory is non-local and it's contextual. And so, yeah, they have no problem with the Frauchiger paradox at all because they just give up on non-contextuality. You can also, inside this, there is also non-meta-contextuality that is underlying here. And non-meta-contextuality is actually just the Wigner-friendification of non-contextuality. And so if you are like me, you want to talk about meta-contextuality, you're also super fine with Frauchiger-Renner paradox. There is no paradox at all. And so the conclusion, if you drop non-meta-contextuality, the conclusion of the paper, of the Frauchiger-Renner paper, that is a self-referential use of quantum theory's contradictory claims, is not surprising at all. Because if you just acknowledge that quantum theory can only be applied in a defined meta-context, that the use of quantum theory is meta-contextual, then there is no surprise at all. Okay, so yeah, of course, you can also use the same picture with the loops. I'm not going to stay here because I want to go to the conclusion. So here is my point. Analyzing the measurement problem as a logical error is avoided when you introduce undiscriminated cuts that you can put everywhere. This idea is not new. I don't have the time, but if I had, I wanted to show you a little bit of literature just to show you that I have completely stolen my idea from other people. That are old ideas that were made in the 70s, 80s, 90s. I don't want to take too much time to talk about them, but if you want, there is a lot of literature that are just comparing the measurement problem as a logical error and analyzing more rigorously than what I'm doing, comparing the measurement problem with Gödelian theorem and trying to say that measurement problem is just a self-referential problem. So there's this paper from Perez and Zurek where they conclude that also quantum theory can describe anything. A quantum description cannot include everything. And so quantum theory is universal, but it is not closed. And this is really important, is that here I'm also arguing for some form of incompleteness of the theory, but it's not an ontological incompleteness. It's a metaphysical or logical incompleteness. It's the fact that the theory is not semantically closed. It cannot be universally valid if you want to, absolutely universally valid if you want to talk about measurements. So you have a form of incompleteness, but that I don't interpret this incompleteness as something that is ontological, like the Bohmian do for instance. There is this paper that is really, really cool by Dalla Chiara, who is really comparing set theory with quantum theory. And so I won't take the time to dive into this, but so you have a logical inconsistency in both. For set theory, it's the Russell antinomy, and for quantum theory, it's a measurement problem. And so she derived the logical inconsistency from two assumptions and derived three kind of solutions. And she compared each time what's happening in set theory and what's happening in quantum theory. And in my opinion, it really makes sense. And this is a really interesting paper. And so, the interpretation that I'm defending, so meta-contextuality, corresponds in her paper to what she called the Feynman interpretation, where the evolution of the compound system is not governed by Schrödinger equation, and any apparatus which realizes the reduction of the wave function is necessarily only a meta-theoretical object. But it can be any object in principle, of course, a priori. And she also, of course, she also compared this. So she said, such a conclusion does not sound like a subjectivistic claim. On the contrary, it seems to be very close to some similar limitative results that we have accepted in logic, like Gödel theorem or Tarski theorem. And she also points out that I'm quite agreeing with this, that it's a kind of purely logical solution, and if it's sufficient to avoid the paradox, it doesn't give any explanation of what's really physically happening in the box. And for some people, I completely understand that it might be unsatisfactory. And so, yeah, I'm going to end. I'm going to skip this. So just wanted to say it's not new. Now, just to compare it with other solutions. So other interpretation. So again, this is my statement. The measurement problem is a logical error emerging from the fact that the theoretical and the meta-theoretical are not distinguished. The use of the quantum theory is meta-contextual. This is my claim. So in GRW, they talk about they have some kind of cut, but the cut is completely ontological. Okay, and they introduce it by modifying quantum theory, and it's a cut that is has completely different nature and is even, I would say, justified in a completely different way. But what is interesting of us with GRW is that it's a true physical theory. You can refute it, you can test it empirically. So still, yeah, of course, it's a really interesting. So it's not an interpretation; it's an interesting new physical theory. The Bohr-Bohm, it's quite funny. I have, of course, I don't want to, to have some issues with Bohmians, but in my opinion, they just embrace the paradox. They just made the paradox ontological. And what do I mean by that is that the theory is completely, really strongly contextual, not in the metaphysical sense that I'm presenting, but in an ontological sense. They say nature is contextual. And this is weird, but why not? The big difference with what I'm defending here is that the incompleteness that I derived here and analyzed from a logical point of view, they just interpret it straightforwardly, and in my opinion, maybe it's too quickly. They consider it as to be something that is ontological. So there is something missing, but I'm deriving the thing that something is missing is not some kind of object that we are not describing. It's just a conclusion from a metaphysical statement, and of course I'm not saying I'm right and they're wrong, of course, but it's another take on the same issue. And Everett and many worlds, in my opinion, is just quantum theory from inside, and it's perfectly consistent in that way. They don't have measurements. They're not talking at all about meta theory, so no projection at all. And I think that if they stick to that, it should be perfectly normal, but you cannot talk about, so you should not talk about observer measurement, because if you do that, well, full measurability fails due to self-reference. It's from the Breuer's theorem. And so this actually justifies the introduction of worlds, because what they do that I don't do is that they interpret quantum state as ontological. And if you do that, of course, you want to define some kind of concept to describe what it is. And so, it's just quantum theory from inside with different worlds, and actually the world explain why also we didn't have full measurability. You of course cannot measure the wave function of the universe, of course. And and also CSM, so context system and modalities. So it's Alexia Favre-Granger interpretation. So after some long discussion with Alexia, I figured out that they have the kind of same logical cut that I'm defending here. But what they do, and I don't do, is that they made it ontological based on empirical evidence. And I'm not particularly fond of it, but why not? But they want to say more. They want to be more realist than I am. And so they want really to add some ontology. And so their cut is not, at the end, is not the same, because it becomes ontological. Okay, I'm going to almost end here. I'm really close to the end. Sorry if I'm a little bit long. Now, of course, I'm going to just talk about the heirs of Copenhagen, the new Copenhagenish interpretation, because of course, this is what I'm kind of defending here. So recently, Matthew Leifer gave a talk where he was comparing objective and perspectival Copenhagen interpretations. I'm not sure if I agree with what this separation. So according to him, there are two kinds of Copenhagen interpretation. There is the objective ones where there is an objective fact on the matter about what an observer observes. And there are the perspectival ones where he says that, well, what is true depends on where you are sitting. I'm not sure that this class actually exists, but if it's right and if it exists, and as he said, this new hybrid paradox, so the Wigner-Franz paradoxes, they are some kind of no-go theorem for this case. If you are Copenhagen or neo-Copenhagen, you have to be perspectival. Okay, you have to agree to put the cut anywhere in principle. Of course, maybe more pragmatically, you're not going to put it everywhere, but you have to agree that on a logical point, you can put it everywhere at some point. So there is a fundamental distinction for all this interpretation between the meta-theoretical and the theoretical object. The interpretation that is probably the closest to what I presented you here is Rovelli's relational quantum mechanics, who's made the cut completely democratic. There is also Bruckner's paper on no-go theorem for observer-independent facts, which is really close. It was a huge inspiration for my paper. And of course, Cubism also defend the same idea. What they do more is that they just interpret meta-theoretical objects as Bayesian agents. And that's the only thing they do that I don't do. But on the logical point of view, it's exactly the same. Okay, so this is my conclusion. Of course, you can do a lot of metaphysics from here. It's not the end of the road. So my conclusion is physics paradoxical? So quantum paradoxes, I argue that they are not physical, but emerge from a lack of metaphysical distancing. And what do I mean by that? Just, a lack of metaphysical analysis. And I quite agree with Wittgenstein's sentence that the subject does not belong to the world, rather it is the limit of the world. So every description that you want to make about the world, it's limited by the definition of what is the subject and what is the object. And so to be a little bit, provocative, absolute universality has some kind of godlike flavor and leads to paradoxical features that cannot be said. On the other hand, if you analyze, so this is a kind of Kantian point of view, but if you analyze the fact that the cut is as a transcendental status, that the transcendental status of the meta-theoretical object, well, the classical Boolean description is the condition of possibility of the rendering of quantum events. What do I mean by this is that you have two levels. You have the levels of your theory, quantum theory. And if you want to talk about it, you have to use a classical description. And that is going to be some meta-theoretical statements that are going to be the condition of possibility for the rendering of your theory. But you have to be careful about this, and you have to be aware that you're doing this distinction, because if you're not, you're going to end up with Frauchiger-Renner Paradox and stuff like this. So you have to be the use of quantum theory is still meta-contextual in the end. So yeah, and this is really close to, so Wheeler is probably the first one to have defended this Gödelian Hunch actually. So there is a famous anecdote that says that he went to Gödel's office to try to talk to him about an eventual eventual link between Gödel's theorem and the Heisenberg uncertainty principle. And Gödel, according to the story, just kicked him out of his office. But still, Wheeler's intuition, I really like this intuition, so that physics is not machinery. Logic is not occasionally applied to that machinery. Instead, everything, physics included, derives from two parents and is nothing but cathode tube image of the interplay between them. One is a participant, the other is a complex of undecidable proposition of mathematical logic. Just food for thought to start the discussion. So of course, because if there's, I guess there might be something that you disagree with, but some kind of ideas that we can discuss for the last hour. So a question that I'm from this that I'm asking myself is quantum theory a physical theory? If you think that physics has to give an ontology, my answer is yeah, maybe not, because of course I didn't put any ontology, or I didn't, on the logical point of view, I just stick to quantum theory as a mathematical theory. I don't need to put any ontology here. So maybe quantum theory is not actually a physical theory, maybe. It's also lead me back to the first slide that I showed you about the logic as physics of any object whatsoever. Maybe quantum theory is just a physics of black boxes at the end, or the physics of the relation between black boxes. So it might still be physics, but not physics of entities or physics of quantum particles or physics of the microverse or whatever. Maybe quantum theory is just the physics of black boxes. We can, of course, discuss this sentence. Classical Boolean description is a condition of possibility for the rendering of quantum non-Boolean events. We can also ask ourselves, I am interpreting the cut as something functional. Is it satisfactory? Because when I say functional, what I really mean is I don't want to consider it as ontological, of course. But maybe we can say, I don't know, but maybe we can say more. Maybe we can say, so it's not functional, but maybe it's epistemological, maybe it's metaphysical, maybe it's semantical. And it's just, yeah, goes back to the question, what is an observer? For example, cubism, to them, observer or Bayesian agents. But I don't have to say that. For example, Rovelli is not saying that, but they have the same, they share the same ground. So yeah, there is some discussion, I guess, in the to have here, and also is it a condition of possibility of what? For a property to an object to have a property, for knowing the property, for defining the property, for talking about the property. I think that there is also some work to do here. It also is related with the question of non-interacting quantum systems, and is meaninglessness the only solution? And actually, so yeah, because if I'm saying all that matter, it only makes sense when I have a defined meta context. Well, what's happening when you're not interacting with the system? Can we say something about this, or does it just has no sense? And so Christian actually worked on this in a paper also, quantum relational indeterminacy, and I think that there is a lot of things to talk about this. So yeah, he interpreted the relational quantum mechanics in the light of metaphysical indeterminacy. And I think that, yeah, meaninglessness. So I'm defending meaninglessness, but I guess this is not the only solution, of course. You can, of course, be more realistic than I am. You can also talk about structural realism and stuff like this. And my last point would be, I don't think that anti-realistic or neo-Copenhagen or whatever you want to call them, these approaches and my approach, I don't think that they have to be really take as just interpretations. I think they're just some kind of starting point from a program research. It's like, we want to analyze quantum theory for what it is. When we do that, we don't feel the need to add some ontology. There is nothing to tell us where is ontology or stuff like this. But now that we have understand the problem on the logical, at the logical level, we want to try to go beyond. And this is often what Fuchs is saying about cubism. This is not an interpretation, it's just the start of a program of research. I think that Gisin is also doing something like this when he's talking about reformulating quantum theory with intuitionistic mathematics. Something that I will be really, really fond of, but I don't have the time to do that. But if someone wants to do that, I will be really fond of this work, is to try to reformulate it in the light of sparse-enrolled imaginary Boolean algebra. Alex Ehrenbaum also worked towards this path. He's defending the fact that quantum theory as a theory of formal languages. And yeah, of course, something that will be really, really interesting is that I'm saying you will have quantum theory and a meta-theoretical theory, but when we actually formalize the meta-theoretical theory, can we say more about the observer? Can we define actually in the meta-theoretical theory what is the observer? Because I have not done that, of course. But yeah, this is something that would be really interesting to do or to discuss. And so thank you for your attention.
Thanks a lot, Hippo. Great talk. Thank you. So Aurélien said sorry, he had to leave.
Yeah, so.
I was curious to hear his reaction, but I guess we can have a chat.
Yeah,
with him.
yeah.
So any questions, please raise your hands or let me know your name in the chat.
Okay, yeah, I've got a question.
Okay, you can go, Paul.
Yeah, Hippolyte, that's very interesting, and I did have a bit of a look at your paper beforehand, so which helped a bit. But it's a really nice way you presented it, I thought. I think that what's striking me is this seems to be turning on a sort of analogy between undecidability and indefiniteness, and maybe your reference at the end to Christian and talking about not indefiniteness but indeterminism, but I mean different words for the same thing, really. If I wanted to defend this from a many worlds point of view, what I'd say is, and I know if Lev is still here, he won't agree with this, but I think in terms of what's inside the box, knowing that the box, it has to be causally isolated from the outside, right? So I would be thinking in terms of what's in the box goes into superposition. It goes into an indefinite state. And what's that supposed to mean? Now, it could be taken to mean somehow it's undecidable whether it's 1 or 0, or it could be taken as some sort of just fundamentally paradoxical state, as the way Schrödinger probably, as he introduced it, thought it's just an absolutely impossible state for anything to be in, and it was, what did he call it, a ridiculous state or something like that. But on the other hand, one might hope to have an account of the indefiniteness. And I think, I mean, I was just reading a recent paper by Christian. He gives a very nice, very clear example of indefiniteness, which I don't think is exactly applicable in quantum mechanics, but it's a nice analogy, which is he talks about this red jumper, which doesn't have a definite hue. And there's nothing mysterious about that at all. It's just partly scarlet and partly crimson, so it's perfectly clear. So I would say, from a many worlds point of view, that what happens inside of the box is the measuring instrument splits into one showing up and one showing down. These are on separate branches, but the branching can't get out of the box because it's causally isolated.
Yes, I completely agree, yeah.
Right. So, but I mean, if there were an account of indefiniteness on the lines of what Christian suggested using mereology, then it seems to me that all the mystery disappears completely. You've got a quite clear sort of statement of what's in the box. And just on the sort of overall point, I mean, it's also called the Quine-Duhem hypothesis, isn't it? The idea that nothing is sacrosanct in science. You can go right down to questioning logic, but at the same time, of course, you're trying not to cut as deeply. You want to avoid cutting as deeply as possible, and if you go down to logic, then you're really cutting deep. So it's the sort of last ditch option, I would have thought. Yeah, well, anyway, that's.
Yeah, I mean, on the last point, I would say I want to go as deeper as I can to really try to see where the problem is hiding and something like this, But right. on Everett, I would say, I think I completely agree with you. This is why I'm saying that for many worlds, this is why I talk about quantum from inside. In many worlds, you don't have any incompleteness. In many worlds, it's completely closed because you're describing the wave function of the universe and every object. What I'm saying is that if you want to talk about meta theory or full measurability, it doesn't make any sense, because this, in many worlds, quantum theory is closed. And so it doesn't make any sense to try to put some levels or stuff like this. The observer is just an object like any other object, because it is entangled. So the device is entangled with a qubit or thing like this. But I think I agree with you that there is no indefiniteness in Everett, right? It's complete.
Well, I think there ought to be. I think that's a problem with many worlds, that there isn't indefinite set, because I think at the micro level, the ontology is obscure in many worlds, and because it doesn't. But that's going off target a bit. But I mean, so what I would say, I mean, if you agree with me about the the box, inside the box, the object can branch, and so, you know, there's, and if you've got an account of what it is for, well, there you've got an account of it. It's indefinite, for example. It's in a branch state. It's got one part in inverted commas and another part in inverted commas, with one showing 0 and one showing 1. But to say that there's no measurement, it just seems to me that from the many worlds point of view, when you measure something in an indefinite state, you split into your branch, and that's what happens. That's what measurement involves. So it seems unmysterious to me. You've got measurement, but measurement it doesn't have a single outcome. There we are. That's the difference. But then, of course, it seems to be that having a single outcome, you know, is a fundamental assumption in what you're suggesting, which is fair enough. But yeah.
Yeah. Okay. I see your point. But yeah. So I don't know what to say. I agree that if you want to talk about measurement under my analysis, there will be some issue. But I guess that's when you do the splitting, you don't describe it. It's not a projection, right? So I guess this is how you get out of here. So okay. But so would you say still that, so would you agree with the way I'm defining things, that measurement should be treated as something meta-theoretical, not theoretical, or not? Because
the what should be
measurement is meta-theoretical.
Well, no, I don't think. Well, I mean, from my point of view, it seems that in the many worlds account is completely unmysterious. It's branching, and there we are. I mean, and it has definite outcomes, but it has multiple definite outcomes. That's what. Yeah. Is that so just an alternative sort of point of view, really?
Mm.
Yeah.
Yeah. Okay. Yeah. Thank you.
Lev?
Maybe I have too many complaints.
Sorry.
The first thing, there were kind of, I'm working on foundations of quantum mechanics for many years. And I remember a time, like 20 years ago, that every 2 years there was a conference on quantum logic. Or maybe even every year. And I think, fortunately, it's kind of stopped. It was slightly resurrected lately, and if I understand that you are trying to resurrect this idea.
I don't know.
Quantum mechanics is not clear, but maybe the reason is logic. For me, it's kind of strange, because I would like to use normal logic to talk about everything.
I agree.
And, the problem with quantum mechanics and logic, when you think that observables have values. If you forget about and quantum mechanics, I think the first thing I studied in quantum mechanics, a wave function. So the wave function tells me that x described by a wave function, there is no value for x, it's just There is a wave function of X, probability or whatever, no value of X. Observables do not have values. This is very strange idea to attain values to observables. And if you try it, you'll get all kind of quotient, Specker, whatever. It's all, for me, not to the point. If you study quantum mechanics, you don't talk about values. And if you do talk, you come to all kind of paradoxes, which are not of any interest whatsoever, from my point of view. So this is kind of general attitude. Number two, what I understand from Gödel, undecidable, you need a theory which has infinities. If theory is finite, there is no Gödel theorem. There is no such thing. I don't see where is this infinities in measurement problem. I can arrange a single qubit, a single photon, and a beam splitter, and two outcomes, and I don't see any infinities there. And there is this, from me, as I understand, there is a measurement problem. Formalism of quantum mechanics tells that somehow both A and B present in the formalism, but we see only one of them. And no infinities whatsoever. And but you say that Gödel theorem and measurement undecidables measurement problem are kind of connected. And maybe the finally kind of a small point, which I just it's not very important, but I'm surprised that you have this list GRW, de Broglie, Everett, and you consider them, especially de Broglie, Bohm and Everett, and you kind of say one, it's non-contextual, and another is just something else. I think all GRW, de Broglie, Everett say, forget about measurements, forget about observers. This is theory about physics. I tell you what exactly happens there. In particular, I will understand what's happening when I perform some measurement. But measurement is not a primitive, and there is no, and this is just kind of, I have some, clearly there is some ontology. Now, there is kind of contextuality in Bohm if you want to have values. In some cases, then you know, if you know initial condition of Bohm, you know that the spin, particular device will come up. You reverse the current, it will come down. So this is kind of very much non-contextual property. You say the spin is contextual when you have an EPR pair. But really, the Bohm doesn't want to talk about this. It's the outcome is not, he says there is no value for spin. There is only wave function and Bohmian position. And I can tell you exactly what will happen if you'll tell me which measurement you will do. So I'm not sure that it's the same as Everett. Everett says there is a big wave function, it evolves. I know exactly how, and I have some recipe how to correspond to experience of creatures there. So I don't see the difference. Conceptually, it's strange that you put them kind of different.
Okay, I put this because I was not sure actually. So thank you for the clarification. I was not sure about the Bohm, how to interpret the Bohm with nothing. I was not sure if I could compare it with Everett as some kind of quantum theory from inside or not. But so according to you, there is also they're also giving up on measurement in a sense. So yeah, okay. Thank you for the clarification. On the second point with the infinity problem. So first of all, I'm not saying that Gödel theorem is completely related to the measurement problem, or that the measurement problem or the current speaker theorem is the same thing as the Gödel theorem or something like this. This is why I use, or I didn't, but Sangolias first used the word hunch. It's just a hunch. It's just, there seems to be some kind of analogy, but I'm not trying to derive something that is really rigorously like the Gödel theorem. And actually, of course, as you point out, it's not possible for now. I mean, and in some papers that are more rigorous than what I presented you, so more rigorous on the logical aspect, they actually say and show that there is no Gödel theorem here. So I would agree with your point. So sorry, maybe I was not clear enough, but it's just I'm just talking about analogy, some kind of incompleteness analog to Gödel theorem. There is some kind of infinity in what I presented you, but I'm not sure that this is going to make any sense here. It's the infinite chain of observers, but yeah, I don't think this is related to what you pointed out. So, but I would agree with you. This is not Gödel theorem, and it's just analogy. I'm just interested in analogy. That's it. And on the first point, I'm not a logician. I'm a physicist, and I don't think I'm interested in trying to revive quantum logic or things like this, because as you guessed, I disagree with the first point that was saying that logic is empirical. I kind of disagree with this. I don't think that we have to develop quantum logic. I think that we have to be careful that when we talk, what we are using in our everyday life is classical logic. When we want to talk about quantum theory, well, the Cohen-Specker theorem shows that you cannot do it if you're not careful, because if you do it and you're not careful, you're going to end up with some kind of logical contradiction, because you're talking in a classical sense about stuff that are not classical, that you have non-Booled algebra, and that's it. This is what I'm talking about. So I completely agree with the fact that when we are talking about classical, and I don't want to develop quantum logic. Maybe it's interesting, but this is not what I want to do here. Here, I just want to point out that we have to be careful. When we talk with the classical language. Quantum theory is not classical language. And so if we are too quick and we just put classical language on quantum theory, we're going to end up with logical paradoxes. This is all I'm saying. But I think I agree with your point.
But just maybe, can you tell me specifically, what I'm against is values for observables, which is necessary for all this. Of course, you will say classical language, so the observables have to have values. This is the idea, because I say, forget about values for observables, and then no paradoxes.
Yeah, okay. I guess my point would be, you can talk about values when as you guess, I'm kind of anti-realistic. So when you talk about values, you have to do an experiment. You have to interact. If you don't interact, you don't talk about values. This will be my answer. But I guess we will disagree on that, because I'm not.
No, but then it's related to your examples with Renner, Fraunhofer, extended Wigner, because you have different observers who see different outcomes. And I'm still kind of very confused by why all these things was revived. Clearly, in one stage, observer has two different outcomes, and you have these two, you take, when you have your logical contradiction, you use some of the facts which know some of the observer, and when this Wigner or whatever omnipotent friend makes some experiment on observer, he creates another outcome which were not before. So there is no, it's clearly not legitimate to use all this chain, because in all this experiment, when you make another measurement, so the previous memory, you cannot rely on it, because you make a measurement on an observer, you change his results. So it's in one place you said there is a single outcome for every measurement. When you measure an observer who performed the measurement, you make the single outcome two outcomes, so many outcomes. So it's clearly not. So this stops all this logical line, I think, because I think it doesn't work.
Well, I think I agree with you that the logical line that I'm defending assume single outcome. And if you do that, well, you just give up on non-meta-contextuality. And so you just end up with the logical argument that we have, our description needs a meta-context. And comparing ask questions or comparing values or observation from different meta contexts, in my opinion, is meaningless, or maybe we can say more metaphysically, but it's going to lead to something that is undecidable. I also agree with you that if you drop the assumption that you have single outcome, like probably many worlds do, that you also don't have any issue with this paradox. I just think this is two different solutions. But I want to stick to one single outcome, and you don't stick to one single outcome.
Last remark, I will stop here. When people talk about Wigner, this was the idea of Wigner, that Wigner can measure his friend who measured some outcomes. And Wigner measured that his friend in a superposition of getting two outcomes. So when you consider Wigner friend experiment, how you can add the postulate single outcome, because this is the whole story of Wigner, that there is no one outcome. Tested that his friend has two outcomes, two different outcomes. So this is, I think, complete kind of, I don't understand it. How people continue to talk about Wigner friend and add to this single outcome. There is a contradiction. Wigner tested that this is not so. So you cannot assume this. Never. So even the people who are not many word people, I say whatever, but this is a special case when you arranged many words. That even not a many worder will say that this Wigner has has this apparatus which makes them in this clean superposition. So for some at this moment there are two outcomes. Maybe very fast they will stop to be, but in some moment, it's the moment of measurement of Wigner, there are two outcomes. You cannot assume that there is one.
I think it depends on different stuff. I think it depends on how you interpret the quantum states, because if you interpret it as a real object, I guess you're probably right, but I have not made this assumption here. I think it also depends on how you interpret measurement. Is it a physical process or not? And so my take is that quantum theory does not. So if you take quantum theory from outside, so if you do the distinction between meta object and object, if you do quantum theory from outside, so your theory is not universal, but you can do measurement and you can project and you can have one single outcome in both cases. This just means that you cannot apply quantum theory to the universe. And it also means that, I don't know what I want to add. But if you do quantum theory from inside, then the measurement is just a unitary evolution. And here I agree with you that you might get two different outcomes when you are from the point of view of Alice, for example. But I think that it depends on the assumptions that you're just on what you want. If you are a realist about the wave function, and if you want universality, I completely agree with you that you might have two outcomes. I think it's just a different flavor, it's different point of views. I don't know. You maybe not disagree with me, but yeah, this would be my answer.
Yeah. Okay. Certainly. I think that the physics explain everything myself. Okay, but let me stop, I think.
Thank you very much for your comments.
We still have some time, so I'm going to ask you a couple of questions, but then we can I think one of the things I wanted to ask was, so first let me say, I really enjoyed the talk, really, honestly. I never told you in person. So I think it's very good in, like you're defending very consistently an approach to the theory. So I appreciate that. Of course, I think you know where we might disagree, so I'm not gonna repeat it. But there might be one thing that like someone who read the paper might be sort of worried about, which is maybe what also Lev was pointing to. So one way in which I understood, which might be wrong, the measurement problem, it was the idea that we should not have the word measurement as a primitive. So this is what I thought the part of the problem was. It's not the problem, but it's part of the ideas behind the problem. And so now you seem to be telling me, I think there was a slide where you say that the measurement is a meta level operation or something like that.
Yeah.
Sorry if I'm misquoting you.
No, this is not this guy.
It's quite at the end.
At the end?
Yeah, I guess so. When you sort of giving the conclusion. Yeah, maybe useful to read the quote so that
I guess this will be there. Maybe one of the last slides.
Yeah, I guess so. Yeah, that one.
This one?
Oh. Yeah, the previous one. So the idea is that it's a logical error because there are meta-theoretical and theoretical. So we need to have a cut between meta-theoretical and theoretical operation or something like that. And the idea seems to be that so if that's the case, then it's even more pressing the worry that measurement is a primitive or something like a primitive. Or if it isn't, then I would just simply ask, okay, what's the definition of a measurement? What kind of thing a measurement is? And I think one of the good things about realist interpretations or interpretations is that they want to either like avoid talking about measurements or at least defining what a measurement is unambiguously. And so yeah, I just like I think that there is a worry always in this kind of way of putting the measurement problem, which might not be which might not reflect what the worry many people have is actually. I don't know what you think about that, but it's not.
I think I quite agree with you because the measurement problem is all very, very often interpreted from an interpretation point of view or at least a realistic point of view. And I completely agree that realists don't want measurement as a primitive, of course, or most of them. Or at least they want to, I don't know, maybe consider the measurement process as a physical process that you can describe with your theory. And I completely agree that I'm completely taking a different point, maybe more, I don't know how to call it. I don't know if you want to call it anti-realistic or pragmatic or I don't know. But what I want to say is the measurement problem, well, the problem is that we don't know how to describe the measurement or we forgot that we are doing a measurement. And so I want to interpret the measurement as not something that is part of the theory, but as something that is relating something that is outside the theory, maybe using it, or maybe, I don't know, but something outside, the relation between something outside and something inside the theory. So an object that is outside and an object that is inside. Yeah, and so maybe it's a different measurement problem. I don't know. I don't know. But yeah, I guess I will agree with you that I want to talk about measurement. I want to say, but maybe measurement is not the right word also, because of course, if you take Carlo's interpretation, it's really weird to talk about observer. It's really weird to talk about measurement because an electron measuring another electron doesn't make any sense, right? So maybe measurement is not the right word. I don't know. If you have, because I think that from this logical point of view, you can have different metaphysical takes. You can have a fully anti-realistic takes and say, okay, we are doing measurements because we are scientists. Quantum theory is a scientific theory, and it's human physics. And so when you interact with objects, this is you as a physicist that is interacting with objects and you're doing a measurement. And so this will make sense on this. And actually Cubism is quite close to this because they say, we are Bayesian agents. We want to predict. So it's not measuring. We want to predict stuff. Quantum theory is a tool to predict, and that's it. You can do that from this, starting from this argument that I gave you, logical argument. But you can be more realistic than that. You can be like Carlo, and I think that's one thing that I don't know if he does it or not. But one thing that Carlo should do is to avoid the word measurement, maybe because, yeah, again, electron and measuring electron doesn't make any sense. But I think that you can still talk about a relation between something that is meta-theoretical and theoretical. And in this sense, what is meta-theoretical will be the object that is not treated quantumly, and what will be theoretical will just be the object that is treated quantumly. And of course, you can describe both objects quantumly also. It will be just a different context. So in the world of Carlo, it will be, I think he's talking about not reference frame. I don't remember its terminology actually, but it will be a different relation. But
so I'm very curious about this reply, and I'm gonna just add. So so the reply seems to entail that you can sort of rephrase this problem or rephrase the result you're giving or part of them without mentioning the word measurement, but just by
yeah, I think so.
Okay, that would be something I would be happy to see, because I'm still thinking that much of the things you said are intertwined with.
Yeah, I agree with you.
So it would be a very nice challenge, yeah. Which I
agree. It won't be easy. It will be a challenge. I agree that. So as you know, I have some kind of anti-realistic way of thinking, and so this is why I completely agree with you that my way of presenting things is intertwined, because sometimes even I see it myself. Sometimes I say, but what I'm saying here is completely anti-realistic, and I might not need to use this terminology to talk about this. So I think that you can rephrase it in a purely logical way without talking about measurement, I think. And I think so actually that's, for instance, the study you did, the metaphysical study of what you did about Carlo could also be applied to this same argument in some sense, because you want to say more. So here I'm arguing for meaninglessness, but of course you could want to say more. So yeah, I agree that I'm using some terminologies that are sometimes going towards anti-realistic interpretations, but you could still be more realistic than I am and still be based on the same logical arguments, I would say. But yeah, it will be a challenge.
I would be happy to discuss. Again, yeah. I think if you want, one of the reasons why I took the mission of trying to do metaphysics with Carlo interpretation is because at least I didn't see in that interpretation the problem I mentioned about having measurements as a primitive. So if it's everything about interactions, I can ask the question you have in the last slide. So what about systems that do not interact? I can ask questions that seems to be physical questions. Then of course there are counterintuitive results, but at least I don't have measurements, I don't have observers, which is what worries me. And if you can do the same without measurements, then of course, then I think I see a ground where you can ask metaphysical questions.
So I believe it can. I'm not saying it is, okay. I believe it's possible, maybe it's not, but I believe it. Yeah.
Thanks a lot for the reply, really useful. Other questions? Yeah, sure. Go.
Well, just to say something which might possibly be relevant, because what seems essential in your point of view is this idea of a division between a level and a meta level, and
exactly.
that sort of dichotomy. And if I would define a measurement as just a particular type of entanglement, but it happens to be an entanglement which creates a representation of an outcome. So, you don't get an electron measuring an electron because electrons don't create representations of the world around them. People do. So they have thoughts and they make statements about the outcomes. Perhaps cats and dogs I'm pretty sure they do create representations of, but the whole issue of representation and what constitutes representation in the brain or not, and all that sort of thing, is quite a sort of fluid area and not very well understood. But it can easily, historically has created the impression that a person and a body are different things, that a thought is something, an object, the ontic sort of level or how would you say, yeah, the ontic status of a thought is something different from the ontic status of a brain. And so you get this sort of, you're generating some sort of dichotomy which perhaps, you know, is connected with your sort of level, meta level. I don't know, but anyway, I just wanted to throw that in as a thought.
No, yeah, thank you. It's an interesting comment. I mean, yeah. So one thing that could be also argue about what I'm saying is that, of course, yeah, I'm just dropping the fact that when I'm talking about measurements as a meta-theoretical process, I'm saying this is a projection. And of course, you might disagree with that. You might, so, or you could have, because when you're talking about measurement as entanglement, to me, it's just you're describing it at the theoretical level, right? So because at the end, it will just ends up as the process will end up as a unitary evolution. But
yeah. But then, of course, I mean, yeah, I mean, and it would be sort of.
But well, yeah, I mean, this is also, yeah, you could argue that maybe you can still have two levels without saying you have the projection and yeah. I mean, you might also define two levels differently also, I guess. Yeah, it's interesting. Yeah.
I won't try and pursue it further, but can I say anything more about it? Well, I mean, yeah, you see, the idea of measurement is just a particular type of entanglement. It really does focus on the point that it's particular sorts of objects which do measurement. It's not like electrons. People do measurements, but you know, maybe cats and dogs do measurements. Maybe, I don't know, snails do measurements. But what's at issue is whether the object which gets entangled creates a representation of what it's entangled with. Let's put it like that. That's what it is, which sort of, from the way I see it, is what, if you like, defines that category of entanglement, which is a measurement. Yeah.
Yeah. Yeah, it really need some more thought, but yeah, thank you for the comment. It's interesting.
I have a question from Alberto.
I just wanted to make a couple of observations. First of all, thanks to Hippolyte, it's very stimulating talk. It certainly covers a ramification of topics. And I want to make a comment on Gödel and on Wigner. On Gödel, I would like to remind that his theorem has a plus and a minus. The minus is famous, is the coherence logical system will have undecidable propositions, yeah? But the plus is that if you have an incoherent system, because of Gödel's construction of his proof, it's extraordinarily easy to prove a proposition and their opposite at the same time, no? Mm-hmm. So the structure of the theorem shows that you have although it's a probabilistic empirical test, if you have an incoherent system, you can very easily prove that it's incoherent. If a system persists in time, like quantum mechanics, for 100 years, without having been able easily to show that, there is a quite high likelihood that it's coherent. Yeah. Nevertheless, I think there might be, this suggests that the analysis has to be made on two levels, because on the experimental and the practical and scientific level, there is a clear way to use it, and the coherence is proven by its persistency or effectiveness. While on the descriptive verbal level, and there you have all the interpretations, there might be something that is used with easily generate paradoxes, and then it makes look quantum mechanics as falling in the opposite case of Gödel theorem, which is where inconsistency are easily generated. Yeah, although as Lev clearly noted, these inconsistencies are irrelevant once you use the theory for physics. Yeah, so I think your hunch is maybe to be thought in this way, or like I encourage to revisit taking these two sides of the Gödel's theorem. The other comment is on Wigner and Wigner friends. My understanding, and I encourage as well to think about this, is that Wigner brought this his famous paper as part of a book which is called The Scientist Speculates, which was edited by Isaac Isidore, now called Goods, who was one of the promoter of the first artificial intelligence revolution. He was a member of Turing's team. And the article is about mind-body relationship. So if you actually go and read the article, Wigner tries to explore, is it purely explorative, is not assertive, explore whether in the measurement discussion there could be a mind-body topic. And the post-Wigner analysis is that that part of the article is for most people incorrect. Nevertheless, he introduced this idea of the cat, although he doesn't use this term, and the cat is terribly useful to compare theories of measurement. So is a tool that makes it extraordinarily useful to compare different theories. Yeah? So from this perspective, one has to be careful not to fall back in the mind-body mistake.
I completely agree with you, yeah.
The original article, because it's a strong temptation. And one of the temptations, and Wigner says it in his article, is the fact that when you do repeated measurement on quantum statistics, the knowledge of the future measurement increases. Because as you sample, you need to get the Born distribution. The knowledge of the future measurement increases. That's where the mistake starts. And then there is something in the memory of your head and so on. That's why he goes in the wrong direction. So that mistake should be avoided. Nevertheless, the quantum theory as it is, does not really address this issue which Wigner pointed out in his article. How does it work? The knowledge of the future measurement increases. There's nothing in the quantum theory that says anything about it. So these are maybe the ingredients that are more relevant to do the next step in your analysis, just as my opinion. But thank you very much for the talk.
Yeah, thank you for the comments. It's really interesting. And yeah, on the second comment, I completely agree with you. That's we should be really careful not to fall back, especially in the way. So I guess between physicists or with philosophers, it's okay. We are all careful about our definitions, or I hope we are. And so, yeah, try not to go back to the mind-body debate or try to talk about the collapse of the wave function from consciousness and stuff. Of course, we don't want to go along this path. But I agree with you that we should be careful, at least when we are talking about these ideas, for example, to larger public or things like that. We have to be really careful about that. And thank you for the suggestion at the end. It's interesting. Yeah, thank you.
Yeah, so yeah, an addition to that, thank you for your remarks on mine, but there is nevertheless an issue which is also on the philosopher side, and is that, at least in my experience, one of the biggest challenges of quantum mechanics is that you can talk about it and describe it with all the words and careful you want, but it is almost impossible to teach it properly, to use it, if you don't make the person do measurements, him or herself. That is that one of the transmission challenges are that theory cannot really teach people without making them do some experiments. And that there are certain nuances of the theory that are never properly integrated or understood by the person until an experiment is made. One of the many, differently from, for example, classical mechanics, where today is very effective at teaching. You can teach most of the things without making the person go in the lab and doing the experiment. And so there is, and that's why I was talking about the plus and minus of Gödel theorem vis-a-vis your analysis. That if there is a missing link between words and facts, when you use the words, you very easily fall in the logical system where inconsistencies are very easily generated. And that's one of the big challenges we're facing today, and why foundational quantum mechanics are becoming more and more important, is that we're still in a situation where we haven't found a way to transmit properly the knowledge without asking the person to go in the lab and do the experiment. There are certain things that don't pass. So I think the care has to be kept by the philosopher as well, which by nature is less aware of these challenges. Sorry.
Okay. Thank you for all interesting comments. Thank you. I don't have anything more to say. I quite agree with what you're saying. Thank you.
Okay, I think we asked you enough questions. You might be tired.
I'm a little bit tired, but it was super interesting. Thank you very much for staying and added comments.
There is also a comment I should mention by Martino Trasinelli.
Yeah, I saw it.
Okay. I just wanted to make sure that you saw the paper. Okay, so thanks a lot again, Hippo, for the very nice talk.
Thank you very much for staying and asking questions.
Okay, I'll see you everyone in 2 weeks with Jinan. I hope you'll be around. That's going to be fun too. Very different topic and very different scholar. So yeah, we'll see. See you next week.
Right. See you next week.
2 weeks, sorry.
Bye.
Bye.